So think about this for a second. How does a speedometer in a car know your exact speed at any single instant? Not your average speed over a mile or even over a second, but your speed right now. That simple question, how to measure the rate of change at one specific moment, is one of the absolute cornerstones of calculus. And today, we are going to unpack the amazing tool that makes it all possible.
You know, we all learned how to find the slope of a straight line, right? It's just rise over run. Super simple, and the slope is the same no matter where you are on the line. But what about a curve? Its steepness is constantly changing at every single point. So how in the world do you measure the slope of something that never stays the same?
And that right there is the heart of the puzzle. See, to calculate slope, you need 2 points. But to find the slope at a single instant, well, you've only got 1 point. It's a paradox that stumped some of the greatest mathematical minds for centuries. It honestly feels like it should be impossible, but it's not. Turns out the solution isn't some simple trick. It's a completely revolutionary idea that changes how we even think about a point. We're about to see how we can use a tool that lets us zoom in on a curve, getting so incredibly close that for a tiny instant, it actually behaves like a straight line. It's an absolutely beautiful solution to what seems like an impossible problem. Okay, so this amazing tool has a name. It's called the limit definition of the derivative. Now, I know it might look a little intimidating when you first see the formula, but stick with me. We're going to break it down piece by piece. Just think of this as the master key for differential calculus. Once you really get this, all those other shortcut rules you learn later, they'll finally make perfect sense. And here it is. Look, the most important thing to see is that this is really just a souped-up version of rise over run. Seriously, the top part, the numerator, that's just the change in your y value. That's the rise. And the bottom, the h, that's just the distance between your x values. That's the run. The real magic, the whole secret sauce, is this little part right here, the limit as h approaches 0. This is what tells us to shrink the distance between our 2 points until it's basically 0, giving us the slope at that one single perfect instant. All right, before we start plugging in numbers, just a quick heads up on how you'll see this written. You're going to see f prime of x, dy over dx, and a few others. Don't let it throw you off. They all mean the exact same thing, the instantaneous rate of change, or, the slope of the line that just kisses the curve at one point. Okay, so the theory is cool and all, but let's actually see this thing in action. We're going to walk through 3 examples. We'll start with a really simple one just to prove that it works, and then we'll crank up the difficulty a bit. Time to get our hands dirty. So for our first one, let's take f of x equals 3x plus 2. Now, we already know the slope is 3, right? So this is the perfect test. So first step, we substitute everything into our formula. After we distribute and clean up the numerator, you'll see a bunch of terms just cancel out, leaving us with 3h on top. Then the h on the top and bottom cancel, and look at that, we're left with 3. It works. The formula perfectly confirmed the slope we already knew. Okay, now for a real curve. F of x equals x squared. We're going to do the exact same thing. We substitute. Now here comes the most crucial step. You have to carefully expand x plus h squared, which gives you x squared plus 2xh plus h squared. The x squared terms cancel out, which is great. Then we can factor an h out of what's left on top and cancel it with the h on the bottom. We're left with 2x plus h. Finally, we let h go to 0, and that little h just vanishes, leaving us with 2x. And this is awesome. This gives us a formula for the slope. It tells us the slope of the parabola isn't just one number. It actually depends on what your x value is. Okay, for our last example, which has a square root, we need a special little algebraic trick. Whenever you see a radical, like a square root, pop up in this formula, the key is to multiply the top and the bottom by something called the conjugate. All that means is you take the top part and you just flip the sign in the middle. It sounds weird, but trust me, this is the move that unlocks the whole problem. So let's try it on f of x equals root x. First, we substitute everything in. Now we use our trick, multiply the top and bottom by the conjugate. And here's where the magic happens. When you multiply out the top, the middle terms cancel and the square roots disappear, leaving you with just h. Now that h on top can cancel with the h on the bottom. Finally, we can take the limit as h goes to 0, which gives us our final answer, 1 over 2 root x.
All right, so the concept is brilliant, but let's be honest, the algebra can get a little messy. So let's quickly go over the 2 most common mistakes people make so you can just sidestep them completely.
The first one, and this is probably the biggest one, is how you expand x plus h squared. It is so tempting to just write x squared plus h squared, but that is absolutely wrong. You gotta remember to FOIL it out. X plus h times x plus h. That gives you the all-important middle term 2xh. If you forget that middle term, the h is never going to cancel and you'll be completely stuck. And the second major trap is trying to cancel the h from the bottom way too early. You can't just pick one term on the top and cancel its h. The rule is simple. You have to simplify the numerator first until you can factor an h out of the entire thing. Only then, after it's factored out, are you allowed to cancel it with the h on the bottom.
So, why did we just spend all that time wrestling with that algebra? What's the big payoff?
Well, it turns out that this abstract-looking formula is one of the most powerful tools we have for describing the world around us, especially when it comes to motion. Just check this out. If you have a function that tells you an object's position over time, its derivative, that's its instantaneous velocity. It literally answers the question, how fast is it going right now? And it doesn't stop there. Take the derivative of velocity, and you get acceleration, how quickly your speed is changing. This limit formula is the engine that translates the language of where something is into the language of how fast it's going.
And that really brings us to the final, most important idea. Yeah, we focused on motion, but this concept of an instantaneous rate of change, it's literally everywhere. It can describe the rate of a chemical reaction, the growth of your investments, or how fast a disease is spreading. The derivative is the universal language of change. So the real question to leave you with is, now that you have this tool, what part of your world are you going to use it to explain?